Chapter 5, Section 6, Applications of Quadratic Equations. So what we're going to do is we're going to look at how to solve story problems, applications, involving quadratic equations, which of course means that we have to be able to use what we learned in the last section on solving quadratic equations using factoring. And of course, factoring is what we studied in the first part of this chapter. So we're going to look at problems that involve geometric figures, consecutive integers, the Pythagorean Theorem, and of course that's everybody's favorite, and using a quadratic model where they give you the actual equation that models some type of real-life application. So as we know, with story problems, we want to make sure that we show our work. And the 5-step method that I've emphasized since chapter 2, I've written down again. Read the problem carefully. All right, make sure you know what's given, make sure you know what you're looking for. Then state the variable. What I mean by state the variable, again, somewhere there's an unknown. Maybe you're going to call it x, maybe you're going to call it t, but you tell me what x is equal to. X equals Tim's age, t equals the amount of time, whatever the case may be. And then step 3, that's the key, because if you can get step 3, you usually can figure out steps 4 and 5. Step 3 is to write an equation that models the problem. So you're going to interpret and convert the words into symbols, mathematical symbols. We've done quite a bit of that, but that's still typically a trouble spot for students. Then once we have this equation, as we learned in the last section, we're going to solve the equation using factoring. And then once we have our answer, we're going to write it out and make sure that it, first off, not only does it make sense, but we're going to write it out in a short sentence, and we're going to make sure that we use any proper units of measure. Feet, inches, minutes, hours, whatever the case may be. All right, so now the first example, which involves a geometric figure, I've got all the steps written out. I'm just going to go over them with you, and I'm going to try to emphasize the importance of the order of the steps. All right, so a right triangle has one leg that is 3 meters shorter than the other leg. The triangle has an area of 54 square meters, and you're to find the length of the legs. Well, you have to know a couple of things. First off, you have to know what a right triangle is, and of course a right triangle is a triangle that has a right angle, and I've drawn a picture of that, and I've represented the right angle there with the little symbol. And the nice thing about finding the area of a right triangle is that the legs represent the base and the height, because remember how the altitude is the perpendicular distance from a vertex down to the leg. So I have that perpendicular distance there. So now I am going to label what the information that's given to me, and it says it has one leg that is 3 meters shorter than the other leg. So if I let x be one of the legs, then the other leg is 3 meters shorter. Shorter means subtract, and I'm going to write x minus 3. So in this case, this is kind of like my base. I always like to call the one at the bottom the base, just like a basement. And this will be my height here. It's perpendicular to the base. So over here, I state my variable. I'm going to let x be the base, or the length of the base, and I'm going to let x minus 3 be the measure of the height. So I've got the base, I've got the height, and I know that area is 1/2, for a triangle, is 1/2 times base times height. So I'm going to plug this information into here. Now remember, they also give me that the area is 54 square meters. So when I go to write this out, I have my area formula, 1/2 times base times height. I have 54 square meters for my area. So in for A, I put in my 54. There we go. And then in for, of course, the half is a half. In for my base, I put the x. In for my height, I put the x minus 3. All that came from over here in the problem and in the diagram. So now I can simplify this. Now, I'm really not crazy about a fraction. The reason I don't want a fraction in there is because it's very difficult to get practiced up, let's say, factoring trinomials that have rational coefficients that are, regular fractions like a half. So I am going to multiply both sides by 2 to get rid of this fraction. So 2 times the left side, 2 times the right side, and of course this 2 cancels out with the 1/2. So 2 times 54 is 108, and of course x times x minus 3, I would have to distribute. And I flip-flop the sides. I brought this over here, so x times x is x squared, x times minus 3 is minus 3x. and then the 108 there. Now there's my quadratic equation, and that's what I have to solve. Okay, but to solve this, as we know, hopefully we know, we have to have it in standard form. So I'm going to get rid of the 108 over here on the right because I have a positive lead coefficient. And so I'm going to subtract 108 from both sides, and I get this guy. These cancel, it just gives me 0. Now comes the factoring step. I'm going to break this down with an x, and I have to think of two numbers whose product is negative 108, whose sum is negative 3. And as you can see, it's negative 12 and positive 9. And so I'm going to have a minus 12 and a plus 9 here in my factors. Now I'm going to set each one of these equal to 0. This is the zero product property. The zero product property, something times something else gives me 0. One of those somethings have got to be 0, if not both. So I set the x minus 12 equal to 0, or the x plus 9 equal to 0. Now these are nice little simple linear equations, which I solve. Here I add 12 to both sides, and here I'll subtract 9 from both sides. And I get x equals 12, and I get x equals negative 9. Now, you may see over here I've made a note. X equals negative 9. Remember, x is the length of the base. Can't be a negative number. So we're going to toss this guy out. And we're going to keep the 12. Now, if x is 12, remember the height was x minus 3. So that's going to be 12 minus 3. Excuse me, which is a positive 9. And remember also that the area was in square meters. So the length of the base and the length and the measure of the height are going to be in meters as well. So x is 12, and that's the base. The base is 12 meters. The height is 9 meters. So what's the question asked? Back to the original problem. Find the lengths of the legs. The legs of the triangle are 12 meters and 9 meters. It doesn't matter which order you put them in, but you do need to use the units. So let's go over those steps. 5-step method. First, read it carefully. State your variable. Write an equation that models the problem. Solve that equation. And then formally state your answer. That's the 5-step method. You've got to get used to doing this. When you go on and take a class in college, like a Math 124 or 126, there's a pretty good chance you're going to get an instructor that's old school like me, and he's going to want to see, he or she's going to want to see all the work. And you can't go wrong if you use these steps. At least I don't think you can. All right, next guy up. Now this one we're going to work out together here. But before we do, I want to talk a little bit about the idea of consecutive integers. Now we did this, way back in chapter 2. We did consecutive integers, consecutive even integers, consecutive odd integers. If I have consecutive integers, that would be like 17, 18, 19. They're one right after another, one bigger than the next. If I have consecutive even integers, they would be like 18, 20, 22, 24. They're consecutive, but they skip the odd number, so they're every other number. So that means if I have one number, to get to the next, I would have to add 2. To get to the next one, I'd have to add another 2. To get from 18 to 20, I add 2. To get from 20 to 22, I add 2. And similarly with odd integers. If I have consecutive odd integers, let's say I have negative 55, negative 53, negative 51, negative 49. I'm adding 2 each time to go from one to the next. So for consecutive integers, if the first integer is x, the next one would be 1 bigger, x plus 1. Then 1 bigger than that, x plus 2, if they're consecutive integers. But if they're consecutive even or odd integers, then we let x be the first even or odd integer. Then x plus 2 would be the next, and then x plus 4 would be the next one after that. So we're going to use these ideas to solve some problems here, and here's an example. It says here, let me move it up a little bit, the product of the first and second of 3 consecutive integers is 2 more than 8 times the third integer. Find the integer. I think that's supposed to be integers. Find the integers. Well, that's a lot there. There's no diagram to draw out, but since I am talking about consecutive integers, and I have 3 of them, I'm going to go ahead and state my variable. I'm going to let x be the first integer, if I can spell, and then x plus 1 would be the second integer, and then x plus 1 or x plus 2 would be the third integer. Now, I'm going to be able to probably model this problem with an equation, but I'm going to have to rely on this. X is my first, x plus 1 is my second, x plus 2 is my third. So now I'm going to bring this up, and then I have more space on this piece of paper here. Here we go. And I'm going to see if I can write an equation that models it. And it all really comes from the very first sentence over here. The product of the first and the second. Now, product means multiply. Well, you can't see that, can you? There, we got it. The product of the first and the second of three consecutive integers. Product means to multiply the first and the second. The first one and the second one. So if I multiply x times x plus 1. This says that this is, and of course is means equals, 2 more than. Now 2 more than means I'm adding 2, so I'm going to put a plus 2 here on the end. 8 times the third integer, that's this guy. 8 times the third, so I'm going to have to put them in parentheses because that way it's 8 times the entire third integer. Now that one took a little bit of thought. I've practiced these quite a bit over the years, so I'm decent at it, but it takes a little bit. You have to read it carefully, you have to state your variable, and then you have to really be careful interpreting these words into symbols. But now I'm at a point that I'm ready to solve my equation, so I'm going to have to simplify both sides. So on the left side I distribute, I get x squared plus x. On the right side I also distribute, and I get 8x plus 16, and then of course the plus 2. That doesn't get multiplied by the 8 because it's not in the parentheses. And I can combine these here. So I'm going to have x squared plus x equals 8x, looks like plus 18. Now that is a quadratic equation. You can see the x squared there. I'm going to move this away and then move this up a little bit. But to solve this, it must be in standard form. So I'm going to have to get everything either on the left side or on the right side. And I like the left side because my x squared has a positive number in front. Even though it's not written down, it's understood to be a positive 1. And that makes it easier for me to factor. So I'm going to get rid of the 8x and the 18 that are on the right side. Now to do that, I'm going to have to subtract 8x and 18. I'm going to do that from both sides. So here's the left side. I'm going to subtract 8x and 18. And on the right side, I'm going to subtract 8x and 18. So minus 8x minus 18. On the left side, I have like terms here. I get x squared minus 7x minus 18. On the right side, everything cancels, which is what I had intended, and I get 0, and I have it in standard form. So now it's just a matter of seeing if I can factor this to finish solving the equation. Let me move this up just a little bit there. So I'm going to break it down with an x and an x. And I need two numbers whose product is negative 18, but whose sum is negative 7. And I'm thinking negative 9 and positive 2. Negative 9 and positive 2. So if I put a minus 9 here and a positive 2 here, I said x minus 9 equal to 0. This is the zero product property. I said x plus 2 equal to 0. Here I'm going to add 9 to both sides. I get x equals 9. Here I'm going to subtract 2 from both sides. I get x equals negative 2. Now, unlike the last problem that involved measurements and we were able to toss out the negative number, I can't do that here because negative 2 is an integer, so that could be a good answer. And I can't toss out the positive number, it's an integer. So if one of these had come out to be a fraction, I could get rid of that, but in this case they're both integers. I'm going to have two sets of answers. That's happened sometimes with a quadratic. So first things first, let me go back and make sure that I didn't miss a word like positive. No, it just says the product of the first and second of three consecutive integers. So it does not say positive. So let's go back to here. Remember, can you see that? I think you can barely see. I'll just have to angle it in. Remember, you have x, x plus 1, and x plus 2 for my first, second, and third integers. So here, x plus 1 would be 10, x plus 2 would be 11. Over here, x plus 1 would be negative 1, x plus 2 would be 0. So it looks like I have three sets of integers. I'm kind of interested to make sure that these are correct. So I kind of think, all right, if I take the product of the first two, that would be 90. And then I take 8 times or 2 more than 8 times the third, that'd be 88 plus 2, that'd be 90. So if I take the product of these two, that'd be negative 2 times negative 1 would be 2. And then I multiply 8 times the third and add 2, that'd be 2 also. I think I got 2 sets of good answers. So the 3 consecutive integers are 9, 10, and 11, or negative 2, negative 1, and 0. So I have to write down both sets of answers. I don't think we've ever encountered a problem quite like that where we had 2 distinct sets of answers. All right, so let's go on to a Pythagorean theorem example. Now you may have to refresh your memory just a little bit about the Pythagorean theorem. It is probably the most famous of the geometric theorems, named after a mathematician that lived back in the days of ancient Greece named Pythagoras. Now, you get the Pythagorean theorem typically in like 7th grade or 6th grade or 8th grade or something. Depends what math class you have. And then, of course, you get it in geometry. But I'm going to go ahead and formally state the Pythagorean theorem. It's right here. If a right triangle has longest side hypotenuse of length C and the other two sides, which are called the legs, of lengths A and B, then a squared plus b squared equals c squared. A squared plus b squared equals c squared. Remember, you have to make C the longest of the 3 sides. That's the hypotenuse for you to use this idea here. Now, I'm going to use this guy to solve a story problem that I just happen to have right here. The hypotenuse of a right triangle, let's make sure you can read it, is 3 inches longer than the longer leg. The shorter leg is 3 inches shorter than the longer leg. Find the lengths of the 3 sides. I'm definitely drawing a picture. So here's a right triangle. I'll say, just based on my diagram, this is the shorter leg, this is the longer leg, and this is clearly the hypotenuse. So it says that the hypotenuse is 3 longer than the longer leg. I'm going to let x be the length of the longer leg here. And that would mean that the hypotenuse is 3 more than that, so that would be x plus 3. And then it says the shorter leg, this guy, is 3 shorter than the longer leg, so this guy would be x minus 3. So over here, I'm going to let x be the length of the longer leg. I'm going to let x plus 3 be the length of the hypotenuse. And I'm going to let x minus 3 be the length of the shorter leg. Okay, well, this is where the Pythagorean theorem comes into play, because you can use the Pythagorean theorem, which talks about the relationship of the 3 sides. Remember, a squared plus b squared equals c squared, c being the hypotenuse, so you could say this is your a, and this is your b, and this is your c. A squared plus b squared equals c squared, so a is x squared. B would be x minus 3, so all of that, x minus 3, that whole thing gets squared. That's a little tricky, because I think students have a tendency to want to shortcut this. And then the hypotenuse is x plus 3, it gets squared, so it's in parentheses. Now, this is not x squared plus 9. You have to do FOIL. Remember, it's x minus 3 times x minus 3. Now, back in an earlier chapter, we talked about special products, including squaring binomials. And there's a pattern. You take the first term and you square it, then you keep the same sign, then you take double the product, and then it's always, always, always a plus, and the last term squared. But people have a tendency to forget that, so you can just do FOIL. And you will get x squared minus 6x plus 9, and x plus 3 times itself, this is a little scratch work over here, is x squared plus 6x plus 9. So this is x squared plus, this is right here, x squared minus 6x plus 9. It's real easy to mess up if you're not careful here, squaring these out. And then x plus 3 squared is x squared plus 6x plus 9. There we go. And I definitely have a quadratic here. I've got 3 terms with x squareds. These two can combine. They're like terms. And then over here, there's really no like terms over here. But I have x squareds on both sides. Here I have 2, here I have 1. I'm going to get rid of this one, because if I get rid of this one, I'm going to have a negative in front of my x squared. So this is going to be, I'm just going to write it out the weird way here. I'm going to stack it up. I am going to subtract x squared and 6x and 9 from both sides. All of this over here on the right cancels out. I get 0. But over here, the only thing that cancels out are the 9s. Here I have 2x squared. Well, that's a squared there. Sorry about that. Minus 1x squared is x squared, and minus 6x is minus 12x. So there's my quadratic. That doesn't have a constant term, but that's okay. I can do a GCF. My greatest common factor is x. I'm going to set x equal to 0, and I'm going to set x minus 12 equal to 0. Well, this is solved, and here I would add 12. So I get x equals 12. Well, unlike the last problem that had 2 sets of answers, this one's only got 1, because x can't be 0. It's the measurement of a leg. Way up here. Throw him out, it's got to be 12. So let's go back. X is 12. So this guy here is 12. This guy here is 12 plus 3, that'd be 15. This guy is 12 minus 3, that'd be 9. So I have to write this out, find the lengths of the 3 sides. And this is, by the way, this is in inches, because you can see it's talking about inches here. So the lengths of the 3 sides of the right triangle are, let's see, I'll put them in order. 9 inches, 12 inches, and 15 inches. And that's good enough. You don't have to say that that's a leg, and that's a leg, and that's the hypotenuse, because they didn't really specify that when they asked the question. They just wanted to know the lengths of the 3 sides. Now you could check this. Does 9 squared plus 12 squared equal 15 squared? It does, but if it didn't, then that would be a good check that said, got to go back and redo this problem. You made a mistake of some type. All right, now I have one last example, which is probably good because you guys are probably getting tired of all this work in these problems. But this is one where they actually have given you the model and you use it to answer a question. So in this case, it says the number y of impulses fired after a nerve has been stimulated is modeled by y equals the opposite of x squared plus 2x plus 60, where x is in milliseconds after the stimulation. Okay, when will 45 impulses occur? So somewhere, somebody has done some research, and I guess that they have done enough tests that they have determined that the number of impulses fired by a nerve, after a nerve has been stimulated, is modeled with this equation. Let me write her down again. Y equals the opposite of x squared plus 2x plus 60. X is the number of seconds, and y is the number of impulses. Now the question says, when will 45 impulses occur? When, that's the time. So I'm going to let x be the number of milliseconds. Can you see that? I think you can. However, let me bring that down a little bit. X is the number of milliseconds for 45 impulses. And the number of impulses, 45, that's y. Y was the number of impulses. So I'm plugging 45 right in there for y. I get 45 equals the opposite of x squared plus 2x plus 60. I'm solving for x. That's what they're asking for. So now it's just a matter of solving it properly, starting with putting it in standard form. This one's a mess. All right. Now you might be better off, even though I'm not crazy about leaving that negative right away, I'm going to take care of it. I would subtract 45 from both sides to kind of cut down on the possibility of silly mistakes. Plus 15 there, and then I would multiply both sides by -1. Now, of course, that's going to change all the signs, except here, -1 times 0 is just 0, but here, when I distribute, all the signs are going to change. I'm going to flip-flop the sides. I'm going to put the 0 here. -1 times the opposite of x squared is x squared. -1 times plus 2x is minus 2x. -1 times plus 15 is minus 15. Now it looks like something I'm more familiar with as far as factoring. It's been nice so far on these samples that the factoring hasn't been the most difficult step. Coming up with the equation or just putting it in standard form can be the most difficult part of the problem. So in this case, I need two numbers whose product is negative 15, whose sum is negative 2, and negative 5 and positive 3 come to mind. Now if you say, well, that's easy for you, well, make a list. Negative 15 and 1, 15 and negative 1, negative 5 and 3, 5 and negative 3, and then see which ones have that sum. So minus 5 plus 3, I'm going to set x minus 5 equal to 0. I'm going to set x plus 3 equal to 0. Here I'm going to add 5 to both sides. I get x equals 5. Here I'm going to subtract 3 from both sides. I get x equals negative 3. Well, this one doesn't make sense. This is the amount of time. This is a negative amount of time here if I use this as an answer, and that just doesn't make sense. So I'm throwing him out, and I'm keeping the x equals 5. So now all I have to do is answer the problem. The problem is, when will 45 impulses occur? 45 impulses will occur after 5, and this was in milliseconds, ms, according to the problem here, ms for milliseconds. And there you go, that's your guy. Now, this is not every single kind of problem that you would ever be able to use a quadratic equation to help you in the process of solving it. There are so many different kinds of story problems, but as far as this book is concerned, these are some of the more typical ones. So I wanted you to see at least one example of each, and of course, there's stuff in the notes, there's examples in the textbook as well, because the more examples that you can look off of, usually the less surprises you'll encounter when you're solving these problems. And as always, practice, practice, practice.